Friends, all is well. Welcome to our science class. Today we are going to start our third part of chapter number 14, that is electric current and its effects. Our topic in this session is magnetic effect of electric current. Magnets are of two types: permanent magnet, which retain their magnetism for a very long time, whereas temporary magnets retain their magnetism only for a short time or until kept under an external magnetic field. We will talk about the temporary magnet first. When removed from the external magnetic field, they lose their magnetism. Now let us understand how a non-magnetic material can be converted into magnetic material by using electric current. The process of converting non-magnetic material to magnetic material is called as magnetization. In 1819, there was a scientist named Hans Christian Ørsted. He found out if you keep a compass near a current carrying wire, then the compass needle deflects to some extent. When current passes through this wire and we keep the compass near that wire, the needle will deflect. This will not work if the current in the wire is feeble. However, in that case, if we remove a part of insulated coating and keep the compass near that region, you will see the deflection. Now we know for a fact that if we keep this compass at rest away from any other magnet, then it will align itself in the direction of Earth's magnetic field. That is, the red part will point in the north direction, while the other part will point in the south direction. What will happen if we bring any magnet near this compass? Well, if we bring the north pole of a bar magnet near the red needle, the needle will show deflection. The needle now aligns itself in the direction of the magnetic field of this bar magnet. We know that in a bar magnet, the field line emerges from the north pole, curve around the magnet and ends itself at the south pole. So, if we move the compass in the direction of the magnetic field, then its needle will also align itself in the direction of the field. With this knowledge in our mind, let's go back to the copper wire. Here, the current flowing through the wire produces magnetic field around the wire, or in other words, the wire becomes a temporary magnet. This is the reason that the compass needle deflects when brought near this wire. Now you know that when electric current passes through a wire, it behaves like a magnet. This is the magnetic effect of the electric current. In fact, an electric current can be used to make magnets. Let us try it out. For this, take around a long piece of wire. It should be flexible wire, and an iron nail about 6 to 10 centimeter long. Wind the wire tightly around the nail in the form of a coil. Connect the free ends of the wire to the terminals of a cell through a switch as shown here. Place some pins on or near the end of the nail. Now switch on the current. What happens? Do the pins cling to the tip of the nail? You can see here the pins which cling to the tip of the nail. And if we switch off the current, the pins are the pins still clinging to the end of the nail? No, they don't. The coil in the above activity behaves like a magnet when electric current flows through it. When the current is switched off, the coil generally loses its magnetism. Such coils are called as electromagnets. Now we have learnt what an electromagnet is. Any conductor such as a straight wire through which electric current flows is known as electromagnet. That's because there is a magnetic field around it. However, we can make magnets strong by wrapping the wire around a piece of iron such as an iron nail. even if the current is same in both the cases. Wire wrapped around iron nail will result in strong magnetic field. Now, there are some factors on which the strength of magnetic field depends. The current flowing in the wire is one of them. If we increase the flow of the current in the wire, the strength of the electromagnet of this wire also increase. Is there any other way? Yes, there is. Another way to increase the strength of this magnetic field is by increasing the number of turns of the wire around the nail. More the number of turns, stronger the magnetic field will be. Now let's see about few applications of this electromagnet. You must have seen large machines lift up car. They have an electromagnet in them. This electromagnet is so strong that it can lift the whole weight of the car. Electromagnets are also used to separate metal objects from a pile of junk. Now what if I tell you that they are used in the fastest trains around the world? Yes, the Shanghai Maglev train is escorted as the world's fastest train, and it works on the concept of electromagnetism. Let's understand the use of electromagnets in simple devices such as an electric bell. Most of the bells that we see nowadays are electric bell. Here is a very simplest diagram of an electric bell. You can see on the screen. This is the inner structure of the bell. Let me first tell the names of its basic components. First is a push switch, which is nothing but the switch we press when we ring the bell. Next, a coil of wire that is wound around an iron piece. There should be two coils of wire wound around an iron piece as well. This coil will act as an electromagnet when the electric current flows through the circuit. Next is a battery and a striker. This striker strikes the gong. That's when we hear the sound. So we can see that this is a circuit. Is it a complete? Why it is not complete? Well, we haven't pressed the switch yet. When we push the button, the circuit gets completed and the current flows from the positive to the negative terminal. You can see in red color that the current flows from positive terminal to the negative terminal. But when the current flows through the coil, it becomes an electromagnet. This electromagnet then attracts this soft iron towards it, and in the process the striker strikes the gong and the sound is produced. But notice what happens when the striker hits the gong. As soon as the soft iron is shifted away from its original position, the circuit breaks. If it no longer connects this wire with the terminal of the battery, and when the circuit breaks, the current stops flowing. So this electromagnet gets demagnetized, after which the soft iron goes back to its start position. This process will continue until the switch is open again. As soon as we press the push button, the circuit breaks and the bell stops ringing. That's the basic idea of how an electric bell works. So students, here we have completed our chapter number 13. Hope you all understood it. Okay, thank you.